Hello and welcome to Principles of Mathematics lesson number 17. In this lesson, we're going to look at addition, subtraction, and estimation with rational numbers. We'll be looking at addition of rational numbers with both like and unlike denominators. We'll also look at rational numbers as mixed numbers. We will study subtraction of rational numbers with like and unlike denominators, which will be done in a very similar manner to adding them. Then we'll look at properties of addition and subtraction of rational numbers. Also addition, properties of equality, and estimation with rational numbers. So let's go ahead and dive in. Here's a visual depiction of how we would go about combining two fractions like 2/5 and 1/5 that have the same denominator. That basically means that the wholes that we're considering are broken up in the same manner into the same number of parts. So that's the easiest case when it comes to combining rational numbers. And of course, in the first figure here, we have two of the slices shaded, and this one only one. So when we combine them, we're going to have a total of 3 of the 5 slices shaded. So therefore, the result being 3/5. Here we're handling the same problem, but using a number line. Of course, we break up the distance between 0 and 1 into 5 equal parts. Notice that will require 4 tick marks in the middle. And we put one arrow with the end at 0 and the tip ending at 2/5, and then without a gap, we continue with another arrow with the size of 1/5, and of course, where we end up is going to be 3/5 once again. As we have seen, basically, when we want to combine two rational numbers or two fractions with the same denominator, we're going to basically keep the same denominator because we're not going to be changing the way the whole is broken up, and we're just going to combine the numerators, so a plus c over b. Now, in the event that the denominators are not the same, there's no need to panic because all we're going to do is we're going to find the common denominator between the two denominators by simply multiplying the denominators. That's the fastest way. And then obviously, because we had to multiply b by d, we have to do the same to a here. That's where we get this ad from. And since d needs to be multiplied by b, we do the same to c multiplied by b as well. And that's where we end up with the cb here. So not that difficult, just requires a little bit of more work. Notice that if it's possible for the common denominator, which is what BD is called, to be handled in such a way that it's the least common denominator. For example, if B and D have some common factors, oftentimes we try to do that and find the least common denominator rather than just the product of the two denominators. We'll get to that later. So here we can see 2/3 being added to 1/4. This is going to require us to break both of these up into 12 parts, which is the common denominator of 3 and a common multiple of 3 and 4. And then it's possible to meaningfully combine those two fractions with the 1/4 here being represented here with 3/12 and the 2/3 here being represented here with 8 of these being shaded, or 8/12. That's how we end up with 2/3 plus 1/4 being the same as 8/12 plus 3/12, or now we can just, because the denominators are the same now, we can just combine the numerators and keep the common denominator, so we get 11 over 12. All right, as I said, our computations end up being a little bit simpler to deal with if we actually, rather than just multiplying the two denominators, quickly find the common denominator first. Now here we're dealing with some pretty simple numbers. 15, for example, we know can quickly be factored using 3, 5, and 5, 1. So 15 is just 3 times 5. And 21 is just going to be handled with 3, 7, and 7, 1. So in other words, 21 is just 3 times 7. So using our LCM algorithm, we find the LCD, which is the least common denominator, to be, we need a 3, we need a 5, and we need a 7. Remember, just multiply the highest power of every factor that you see in both factorizations. So 3 times 5 times 7, you never want to repeat. So that's going to give us 15 times 7, which we can figure out like this. 7 times 10 plus 5, that's a quick way. This is using some of the techniques we've learned already. So we get 70 and 35, which gives us 105. So we know that we want both of those denominators to turn into 105, right? Now, we know that in order to do that, 15 has to be multiplied by what to give us 105? Well, you can easily see that right here because we multiplied 3 by 5 times 7 to get 105. So if we have 15 already, we're going to need a 7. So that means we're going to multiply the 15 by 7. So that means we have to do the same to the 2, right? And for the next one, 21, notice 21 needs to be multiplied by 5 to give 105. So we're going to multiply the 21 by 5, which means we have to do the same thing to the 4 on the top. Because of course we don't want to change the problem, we just want to change the way it looks so that we can handle it more easily. So now the new numerator for the first fraction is going to be 14. And the new numerator for the second fraction with the denominator of 105 is going to be 20. So now all we have to do is go ahead and combine the 14 and the 20. So 14 plus 20 over 105. So we end up with 34 over 105. Once you get to this stage, of course, if there is any cross-canceling possible to make this any simpler, you always want to do that. In this case, I do believe these two numbers are relatively prime, so that's as simple as it's going to get. All right, so for this next one, we notice that the LCD is going to be 15. Notice that when you have 2 over negative 3, you can also write that as just negative 2 over 3, right? So, in fact, you can also write it as negative 2 over 3 as well. So these are all the same number, right? So I'm going to deal with the negative sign on the top. Let me go ahead and actually rewrite them. So I'll just put the negative on the side like this, so there's no confusion. So now I know that I want to make both of those denominators 15. So what do we have to multiply 3 by to get 15? That's just 5. So we're going to multiply this denominator by 5. Make sure you do the same to the numerator. And this next denominator we're going to multiply by 3. So we make sure we do the same to the numerator. So now, be careful here because we have negative 10, not just 10. And then plus 3. So we end up with negative 10 plus 3 over 15, which is going to be giving us negative 7 over 15. Now, it looks cleaner if you put the negative on the side, like so, okay? So there's our answer for that one. All right, so for this next one, notice that we could handle this sum first and then add the 1/6, or we could just handle them all at the same time, because for all practical purposes, we can drop those parentheses and just think of this as 3/4 plus 1/5 plus 1/6. So this way we can just handle all three at once. So we need to find the least common multiple of 4, 5, and 6. 4 is, of course, 2 squared. 5 can't be reduced any further. It's just 5 as far as the prime factorization goes. And 6 can be written as 2 times 3. So you notice we're going to need a 2 squared, a 3, and a 5. So the LCD is going to be 2 squared times 3 times 5. Using compatible numbers, we multiply 4 by 5 first to give us 20 times 3 will give us 60. All right, so we're going to want to turn each of those denominators into 60. So in order to do that with the first denominator, you're going to have to multiply by 15. So that's what we'll do. And we'll make sure to do the exact same thing to the numerator. For 5 to get to 60, we need to multiply by 12. So that's what we will do. And we'll make sure we do the exact same thing to the numerator of 5. For 6, we're going to need to multiply by 10. So that's what we will do. And we'll do the same to the one on the top. Okay? So now our new numerators with the denominators of 60 are going to be 45, 12, and 10. So now all we have to do is combine all of those. So 45 plus 12 plus 10, and remember the 60 is just carried at the common denominator. So we get, let's see if we can use some of our techniques. 40 and 10 and 10, that's 60, and then 5 and 2 and 0 is 7, so 67 over 60. All right. Problems that have variables in them are handled in a very similar manner. So if you notice here, the LCD is just going to be xy, right? So we're going to want to turn both of those denominators into xy's so that we'll have the same denominator. So that's going to require multiplying the first denominator x by y, which of course means we have to do the same on the top to the 3. For the second denominator, we're going to have to multiply it by x, which means we're going to do the same to the 4 on the top. So now the new numerators become 3y and 4x. And because we now have the same denominator for both fractions, we can just use our a over c plus b over c equals a plus b over c rule and go ahead and combine. So we get 3y plus 4x over xy. And there is no factoring I can do on the top to make any simplification, so that's as good as it gets, or as simple as it gets, okay? That's how you handle those. Okay, how about this one? Well, with this, the LCD, which is the LCM of all the denominators, is going to require a what? We have a common factor of A and one of B. We don't, of course, for LCM, we don't look at just common, we look at all factors. So, and we pick the highest power of each factor and then multiply. So for A, we're going to take A squared. As always, try these yourself before you watch me do it. I know you've got it down by now. Sometimes I forget to tell you because I'm pretty sure you know it by now, right? And for B, we're going to take B squared, right? So there's our LCD. So we're going to want to make both of these fractions have a denominator of A squared, B squared. So what is needed to turn a squared b into a squared b squared? Notice we only need just a factor of b. So we're going to multiply by b, and we'll make sure to do the same to the 2 on the top. And for the next one, notice to get from ab squared to a squared b squared, all we need is to multiply by a, right? So that's what we will do, and we will make sure to do it to the 3 on the top as well. All right? So the new numerators are 2b and 3a. So now, because we have the same denominator, all we do is we carry the common denominator and we combine the numerators. So we get 2b plus 3a over a squared b squared. Again, we notice that there is no simplification that's possible, either on top or bottom, no factoring possible, so we're done. We make sure we don't cross cancel the b's or anything like that, because these are terms and we can never cross cancel a term with either a term or a factor, so we're done. All right, so what is a mixed number? A mixed number is basically a number that's made up of an integer and a fractional part of an integer. You've seen them, plenty. For example, 3.5, right? When you see that, that's nothing other than 3 plus 1/2. That's all that means, okay? So, of course, notice we can always go ahead and combine those two fractions using our methods. Throw a 1 underneath the 3. So now you need a common denominator of 2. So that means that 1 has to be multiplied by 2, and we'll do the same to the 3 on the top. The other one is already a 2, nothing needs to be done. So the new numerator for the first one is 6, and for the second one it remains 1. So now we just combine them and we get 7/2. So notice that any mixed number can always be written as just an improper fraction using this simple method. Now, once you do enough of these, you get to realize that there's a nice quick algorithm for accomplishing this without having to go through all this. So all you do is you have to remember this graphic. You're gonna multiply those and add it to that to get your numerator. The denominator, of course, stays the same. So keep the denominator. To get the numerator, multiply the denominator by that whole number, so you get 6, add it to the 1, and you get what? You get 7/2. So this is like a nice shortcut method for converting a mixed number to a fraction, an improper fraction, of course, right? All right, because why? Because the numerator is larger than the denominator. A proper fraction like 3/4, of course, being one where the numerator is strictly less than the denominator. They can't even be equal. If you have 4/4, that's not a proper fraction, that's an improper fraction, okay? All right, here are a couple more that we're going to convert. So we'll do it both ways, okay? Let's go ahead and do it the longer way because it's good practice. That's 4 plus 1/3, right? So think of it as 4/1. We're going to want both denominators to turn into 3's. So that means we're going to need to multiply the 1 by 3. We'll do the same to the 4. So the new numerators are 12, and of course the next one doesn't change because the denominator was already 3. So we end up with 13/3, okay? Now the shortcut method was, if you recall, multiply this 3 by this 4 and then add it to the 1 and keep the denominator for the next step. So the denominator stays the same, but for the numerator we multiply 3 by 4, which is 12, and add to 1, we get 13. So of course we get the same result. Now what do you do when there's a negative number? Well, simple. Just keep it on the side, open parentheses, and handle the rest. So This time, since we've done enough of this, let's go ahead and just use the shortcut. So we get 5 times 3, right? Which is 15 plus 2, so 17 over, we keep the denominator, right? Of course, we don't need to write the parentheses. I wrote the parentheses because I initially planned to go through this, but then I realized you've had enough. Let's keep the video, try to keep the video a little bit shorter. So negative 17 over 5, just like that. Okay? All right. All right, so how do we go the other way? How do we take an improper fraction and turn it into a mixed number? And remember, anytime you have an improper fraction, since the numerator is larger than the denominator, larger than or equal to the denominator, you should have a whole number in there plus some fraction, right? So you can always write it as a mixed number. So the one way is just to take the 29 over 5 and to maybe rewrite the 29 as, say, 5 times 5, and that leaves us a 4. So you want to make sure that whatever is left here is going to be less than 5, right? And then over 5, so that's 25 over 5 plus 4 over 5, and we end up with 5 and 4/5. So that's one way of handling it. Now, the most efficient way of handling it, of course, is long division. Just go ahead and divide 29 by 5. So, of course, we get 5 times 5 is 25. That leaves us 4, right? So this is the loop you're going to have to remember. You're going to start up here with the 5, then go here, and then, so 5 plus the 4 over that 5. So you just get 5 and 4/5, same way, okay? So the nice thing about this is, even if your number is really large, like the numbers you're dealing with, like let's say you have 1,234 divided by, say, 345, you can do the same thing using long division, but don't worry, I'm not going to make you sit there and do a bunch of long division problems in the class. So here's what we'll do. We'll do a clever long division. We'll use technology, okay? I'll show you how. Now, we are going to divide. In other words, we're not going to completely rely on technology, but we will utilize it a bit. So let's go 1, 2, 3, 4 divided by 345, right? So we get 3 and change, right? So what we're interested in is the 3. So we put the 3 here, and we go ahead and multiply the 3 by 345. That gives us 1,035. We write that here. Now we go ahead and subtract 1, 2, 3, 4 minus 1,035. So we get 199. And so there we have it. So remember the loop, start here, then go this over that. So this is going to be 3 and 199 over 345, like so. Okay, so a very nice simple way to quickly find the mixed number version of an improper fraction. All right, so practice that with a couple and then we'll proceed, okay? Okay, next we have the additive inverse property, which basically says whenever you have a fraction a over b, there is another fraction which is the opposite of it, and if you add them, so the opposite of a number is also called its additive inverse. So if you add a fraction to its additive inverse, of course, you're going to end up with what? With 0. It's just like it was with whole numbers and integers and natural numbers, right? Well, we didn't have the inverses when we were dealing with natural numbers. We didn't get into it till with like integers mostly, right? So, but if you do this from this direction, you also get 0. So a number added to its additive inverse is always going to end up giving you 0. It's important because we're going to use that fact when we solve equations. So just as in the case of integers, where the opposite of a number was just itself, same thing works with fractions. The opposite of a fraction is the fraction itself. And the opposite of a sum is just the sum of the opposites, basically. That's how we say that. We say the opposite of a sum is the sum of the opposites, okay? And that works with fractions as well. Now, when you distribute, in this particular case, when you distribute the negative into a over b plus c over d, normally we just write it as negative a over b. We go ahead and notice that negative times positive. Remember, there's an invisible 1 that we're distributing, so a negative 1, right? So we just say negative times positive is negative, so we just write minus c over d. Like so, okay? Then we have the addition property of equality, which if you remember with the case of just whole numbers and integers, we just said if a equals b, then a plus c equals b plus c. Now we're doing the same thing here, but in this case we're just using a fraction. So we're adding the same fraction to the equation a over b equals c over d. And we're saying that can be done without changing the validity of the original equation. Now, in other words, we get an equivalent equation to the first one. And this also works with subtraction, of course. A over b minus, we call that the subtraction property sometimes, but it's just a different version of the addition property, right? Adding to the opposite. So a over b minus e over f is also equal to c over d minus e over f. Okay. Okay, subtraction of fractions works exactly like the addition. So we just need a common denominator. So we're going to realize that the LCD of two denominators 4 and 8 is just 8. So we're going to make both of those denominators turn into 8. The first one is already 8, nothing needs to be done, so the 5 doesn't change on the top. 4, however, needs to be multiplied by 2, so we do the same to the 1. So the second numerator changes to 2. So now we just subtract across, so 5 minus 2 over 8. So just as we have a over c plus b over c equals a plus b over c, we have a over c minus b over c equals a minus b over c. Same method. Okay, so we end up with 3/8. Now, when it comes to mixed numbers, the safest approach is to turn them into improper fractions. Go ahead and subtract them, and if you want, you can go back to mixed number form for the answer. So the first thing we'll do is we'll quickly turn these into mixed numbers. Remember, the denominators stay the same. The numerators change, so you multiply 3 by 5, that's 15, plus 1 is 16. For the next one, 4 times 2 is 8, and 3 is 11. So now we go ahead and find the LCD, which is 12, obviously. Now, to turn the 3 into 12, we're going to have to multiply by 4. So we'll make sure we do that to the 16 on the top. To get from 4 to 12, we need to multiply by 3. So we do the same to the 11 on the top. So now our numerators are 64 and 33. We go ahead and subtract 33 from 64. And of course, we end up with 1 and 3, so 31. Now, if the answer is required in a mixed number format, you just go ahead and quickly do the long division. So we know that 2 goes into the, 12 goes into 31 twice, that's 24, leaving us 7. Remember the loop, start on the top, go there, and then over that. So we get 2 and 7 over 12, like so. All right, so make sure you understand all that, and then we'll proceed. All right, so now we just want to get some variables involved. No difference, exactly the same approach. So we need a common denominator, so we know 6 should work, right? So we'll turn both of those denominators into 6s. For the first one, we need to multiply it by 3, so we'll multiply the top by 3 as well. For the second one, we need to multiply the 3 by 2, so we'll do the same to the x on the top. So now both denominators are 6 and the numerators are 3x and 2x, right? We go ahead and now just write the denominator once and combine the 3x and the 2x. So we end up with 5x over 6. Notice that this can also be written as 5/6 with an x on the side like that. They have the same meaning, okay? All right. When you see a fraction and then the variable right next to it, that just means multiply. That's 5/6 times x, or 5x over 6. Same thing. Just make sure you don't put the x on the bottom, because that would not be the same thing. All right. How about this next one? I'm sure you've paused the screen and you've tried it on your own. If you forgot, do it now and see if you can do the next one on your own before you watch. Okay, so we need the LCD, right? So what is the LCD between, or what is the least common multiple of x and 2x squared? Remember, take the highest power of every factor you see and multiply. I see a factor of 2, I need that. And I see factors of x, and the highest power of x is x squared, so there it is. That's the LCD, right? So we're going to turn both of those denominators into 2x squared. So this is not uncommon, where one of the denominators actually is the LCD. So that's not surprising. All right, so now, how do I get from x to 2x squared? What's missing? Well, I need a 2 and an x, right? So we're going to have to multiply the x by 2x, so we make sure we do the same to the one on the top. The next denominator is already 2x squared, nothing needs to be done, so that 1 isn't going to change. So the denominators are both 2x squared now, and the new numerators are 2x and the 1 which didn't change. So now we just subtract across 2x minus 1 over 2x squared. No factoring is possible on the top, so no simplification possible. We know we can't cross cancel those x's or those 2's because 2x is attached to the 1 with that subtraction, so we're done. All right, so many of the estimation and mental math techniques that we used with whole numbers can also work with rational numbers. And of course, estimation plays an important role in judging the reasonableness of computations. Okay, so here we have a 6th grade class which is collecting cans to take to the recycling center. Becky's group brought the following amounts in pounds. About how many? So what does that say? That says go ahead and do an estimation. About how many pounds does her group have altogether? So the amounts given were 1 1/8 of a pound, 3 4/10 of a pound, 5 7/8, and 6/10. Okay, so the way that we approach this is we do what's called front-end estimation, and then we adjust by using one of these fractions as a reference. So add the whole numbers 1, 3, and 5. Those are the only whole numbers we have, right? Because there's no whole number there. So we get 1 plus 3 plus 5 is 9. Now we're going to approximate these based on how close to are to one of these three numbers, 0, a half, and 1. That, of course, is pretty small, so we'll use 0 for that. 4/10 is almost 5/10, which is a half, right? 7/8 is almost 8/8, which is 1. And 6/10 is close to 5/10, which is a half. So adding those gives us a half plus a half, which is 1 plus 1, which is 2. So a good estimate should be 9 plus 2, which is 11. So that's kind of a quick way of estimating these fractions using front-end estimation and then adjusting for the fractional parts using the fractions 0, a half, and 1. Okay, let's go ahead and try to estimate these. Notice that 27 over 13, that's pretty close to 28 over 14, which we know is 2, right? And this one is pretty close to 9 over 9, which is 1. So this is going to be approximately 2 plus 1, which is 3. For this one, now 3 and 9/10, that's quite close to 4, right? So we'll go ahead and use 4 for that. And we'll use 3 for the next and 1 for the last one. That's giving us 8. Or if we want to do it using front-end estimation, we'll go ahead and combine the 3 and the 2. That gives us 5, right? Now we'll adjust with 0, a half, and 1. So this will be 1, right? This will be close to 1, so another 1. And so will this, 11 over 12, 1. So we get what? We get 3. Once again, 5 and 3 give us 8. So either way, right? Okay, so that's how we estimate here. And that pretty much wraps it. This is probably one of our shortest videos. You're going, thank God, right? Well, let's go ahead and look at some homework problems, see if there's anything there that might need some tips. All right, so here we have this meter stick of sort, and it's been broken up into these 4 regions, M, A, T, H. Very clever, right? Okay, so we want to know this number, 26 over 22, would land into which one of those regions. You never want to decide where a fraction lands if it's in improper format. So you're always going to want to take it and turn it into a mixed number, because that will be much easier to determine. So we're going to go ahead and divide 26 by 22, so we get 1 and with a denominator of with a remainder of 4. So we start here and do the loop, right? So 1 and 4 over 22, which is 1 and 2 over 11, right? If we just simplify that. Notice that what we could have done is we could have taken the 26 over 22, we could have reduced it first to 13 over 11, and then we could have divided to get 1, 11, and remainder of 2. So again, the loop will give us what? Will give us 1 and 2 over 11. So of course the problem won't change, but this is kind of a nice habit to be into, to reduce first, because then you'll be dealing with smaller numbers, which is kind of nice, right? But in either case, we know that it's a number between 1 and 2, right? So what region is it going to land in? M. Okay, here we want to verify that each of these statements is true. So all you have to do is just go ahead and take care of the addition on the right side and verify that you get what's on the left side. So just to show you one of them, let's look at the first one, then you can do the rest. So you have 1 over 4 plus 1 over 3 times 4, which is basically 1/4 plus 1/12, right? We need a common denominator of 12. So of course we have to multiply this 4 by 3. We'll do the same to the top. And so the new numerators are now 3. The other one, the denominator, is already 12, so we don't need to do anything to either the 12 or 1. So we end up with 4 over 12, which of course reduces to 1/3. So that's basically how you would go about doing this, okay? That's all. Same goes with the other problems. All right, with something like this, don't let the fractions scare you. We're just solving for x, so we have x plus 4 and 1/4 equals 5 and 1/5. So basically, all we have to do is, to get x by itself, is go ahead and subtract 4 and 1/4 from both sides. So we end up with x equals 5 and 1/5 minus 4 and 1/4. Remember, the safest way to handle these, go ahead and write them as improper fractions. In other words, get them out of mixed number form, then perform the computation. So for this one, we know the denominators don't change. The numerator is going to be 5 times 5, which is 25, plus 1 is 26. For the next one, 4 times 4 is 16, and 1 is 17. So now we need a common denominator of 20. So what do I do to 5 to make it 20? I need to multiply it by 4. So I make sure I do that to the 26. What do we need to do to 4 to make it 20? We need to multiply it by 5. So we do the same to the 17 on top. So the denominators are both now 20. The new numerators are 4 times 26, which we will handle as 4 times 20 plus 6. So that gives me 80 and 24, so 104, okay? Some of these tricks we've learned along the way are really handy. So we get 104 over 20 minus 17 times 5. Can you do that like this? So that's 5 times 10 plus 7. So 50 plus 35, which is, now a lot of times this gets done in your head, but I want to show it so that you can see what I'm thinking. So there is 85, okay? So now we just do 104 minus 85. 5 from 14 is 9. 8 from 9 is 1, right? All right, so we end up with 19 over 20. All right, that's how you do this, and also how you do the next one. Of course, for that one, you're gonna want to add 2.5 to both sides, right? All right, so in this one, we have a teacher that wants to show 2 3/4 is equal to 11/4, and the teacher has drawn this picture and claiming that we can see that this is 11/4, and one of the students is saying, no, this is a picture of 11/12. So what is Ken thinking, and how should the teacher respond, right? Well, it's all about what we consider to be a whole, right? So Ken is thinking that each of these little pieces is a whole. So in that way, if that were the case, he actually would be kind of thinking the right way. But the problem is that the teacher is considering each of these blocks to be a whole, right? So this is why in the beginning of the lecture we had said it's very important what you consider to be the whole that you're studying. And in that case, of course, then you're just dealing with 1 whole and 2 whole and 3 wholes, or we're dealing with 12 quarters, right? 12/4. And in that case, what's shaded is 11 times a quarter, which is 11/4, right? Of course, remember that's 11 over 1 times 1 over 4, so you get 11/4. Okay, so that's the problem with what Ken was thinking. All right, so here we're simplifying, and basically, we've done similar problems in the lesson, so I'll just point out a couple of points about a couple of them. And of course, not all of them are really reducible, except this one, for example, you can just work it out, say that's 16 over 81. There are no common factors, it's not going to simplify any further, right? So this one will just be 16 over 81, and that's that. Now, here, of course, you can't cancel anything, and there is no factoring possible, so this is as good as it gets. This one, however, if you remember, the top is a form of difference of squares. F squared minus L squared equals quantity F plus L times quantity F minus L. And so we can factor that as C plus D times C minus D. And then we have C minus D on the bottom, so we can now cancel all of C minus D here with all of C minus D there. So we end up with C plus D. Make sure you do not do this, which is what unfortunately too many students do in a math class. Make sure you don't do this and say, oh, that's C, that's D. So notice you would get the wrong answer anyway, because you would get C minus D, which is in fact should be C plus D. So stay away from that with all your might. That's completely incorrect. All right. That's about it. You can figure the rest out on your own. All right, so here we want to explain why on a number line, why negative 1 over 100 is greater than negative 1 over 10. So it's a little bit easier if you actually try to understand which one is the larger fraction in its positive format. In other words, let's look at the opposites. Let's compare 1/10 to a 1 over 100, right? Now, you know that if you have two fractions, as long as everything is positive, right? Numerators and denominators. Then if the numerators are the same, which fraction is actually going to be smaller? The one with the larger denominator or the one with the smaller denominator? I mean, very obvious, right? The one with the smaller denominator is actually going to be a larger denominator. Just think about it. 1/10 is 0.1. and 1 over 100 is 0.01. In fact, this one is 10 times larger than that one. Also consider that if you take 1 over 100 and multiply it by 10, you get 1 over 10. So definitely in this case, this is greater than that, right? However, you know that if you multiply both sides of this inequality by a -1, and get negative 1/10 and negative 1 over 100, you immediately have to change the direction of the inequality, right? So you can see that negative 1 over 100 is actually greater than. Remember the inequality sign? The mouth opens toward the larger number. So if you were to read this from left to right, you would say negative 1 over 10 is less than negative 1 over 100, right? If you wanted to read it from right to left, you would say negative 1 over 100 is greater than negative 1 over 10. And that accomplishes our goal. All right, so that should about wrap it for this lecture. And take care of yourself. We'll see you for the next lesson.